Okay, let's look at another OSC app for sending control data. We're going to look at Zig Sim today, which we have a free version, which is Zig Sim. Zig Sim Pro we'll look at in another video, which is about $5 or so. And then the same people also recently came out with this app called Zig Cam, which is sending video over NDI as well as data. But we'll just look at Zig Sim. You can get that on the App Store, and it's so contrary to like a Touch OSC, which allows you to create your own custom layouts, and it's really mostly functioning on this metaphor of like audio applications like faders, knobs, things like that. Zig Sim is accessing the built-in sensors within your phone. So we've got accelerometer, gravity, acceleration, gyroscope, quaternion, compass, pressure, touch, GPS, mic level. So lots of really great sensors that we can access from our phone. To get more info about all of these, if we look, so on their GitHub, we have some description. It's made by a studio called 1 to 10, based in Japan. If we go get started, so it's got description for all of the different types of sensors and a little bit of info on how to use all those. So we'll go through some of these and learn what they do. Let's go ahead and make sure we are connected properly. So like anything else, so we're sending it to the computer here. I need to know the IP address. Let's get system prefs over here. And so I'm connected via USB right now, in order to have a more stable connection. Depending on your Wi-Fi network, if it's just a personal at-home network, it should be just fine. So make sure you're on the same Wi-Fi network with the smartphone and the computer, and then look up the recipient, the computer's IP address here. So that's what you would type into the IP address on the app on Zig Sim. I'm gonna put in the Ethernet address just right here because I'm not connected via Wi-Fi. I'm connected just via USB. So I've already done that. Arbitrary port number. Come back. Arbitrary port number. Return. Thanks. So protocol we can send. So UDP, Universal Data Packet. This is the kind of standards for OSC. TCP is a different. So Zig Sim is absolutely unique. You could choose to write a local file on the smartphone as opposed to sending it in real time to another app. So that's pretty cool. Message format. So OSC format is what we want. JSON, which is JavaScript object notation, can be useful also in other situations. That's also a common way to parse messages between programs like this. So let's just do OSC. Message rate is pretty nice if you have something that's, let's say like atmospheric pressure or something that doesn't really change that often. You can lower that rate to save bandwidth. Device ID, this is automatically generated if you had several smartphones all sending to the same touch designer, let's say. Each would have a unique device ID, which is cool. Compass angle, we'll see when we look at compass. It depends on how you have oriented the phone, basically. And then this beacon thing also is, we're actually not going to look at the beacon, but that's a unique ID for that sensor. So let's dive into an accelerometer. So we've got everything set up. We select which sensor we want. It has a little check mark here. We can do as many as we want all at once, but I'm just going to do accelerometer right now and hit start. And beautifully, that shows up right there. So we can see. So we got X, Y, and Z acceleration. And so we'll notice, so this measures change over time, which is what acceleration is. So when it's at rest, it's mostly hovering around 0. And just as you move it, that's when we see the acceleration. And if we look at gyro also, let's just go ahead and look at both the accelerometer as well as gyro. So these look pretty similar. And actually, you know what? Let's do something. Usually with real-time data like this, it helps a lot to just connect it to a trail chop to see what we're doing. So what I'm going to do, I want to get rid of this. So it also sends the device info. So it kind of just gives it the number. If you have different smartphones connected, each will have a unique device info. So I just want to get rid of that device info channel. So we learned last time, if I do caret, anything called device info, actually I need star before that. There we go. So I just got rid of that. And let's connect a trail. So we can see that, you know, gyro and accelerometer look pretty similar. You know, as I kind of shake it, they respond in a similar way. And you know, both of them are measuring acceleration. So if the phone is at rest, they're basically pretty much zero. I mean, the margin of error there is basically 0.005 plus or minus, so it's pretty much zero. The difference between these would be that the gyroscope accounts for acceleration of gravity due to the Earth, which would be the strongest source of gravity for us. I guess the moon could also affect the gyroscope, but probably like the Earth is affecting that. Whereas the accelerometer data is not affected by that. So accelerometer is purely the movement of the phone without accounting for the force of gravity. So, you know, the subtle differences between these sensors, like a lot of times, you know, sometimes we've seen on like smartphones, there's an ability to undo something by like shaking it. That is typically done with an accelerometer. But let's say in a plane, for a plane to determine its acceleration, they'll use a gyroscope because, you know, knowing the orientation according to the Earth is very important, obviously, for a plane, so it doesn't crash, I guess. So that's those two. Let's just click those off. Let's look at gravity. So this one's pretty cool. Actually, let me just get rid of this. Let's look. There we go. So this is showing the force of gravity, and we can see the z here is -1 because so z-axis is going kind of through the phone, x is like this, y is like that. So there's a negative force going through, which makes sense because the Earth is pulling the phone down towards the table. If I flip the phone over like this, oops, start. Okay, go back. I just turned it off. All right, so now this is positive. As I flip it, now it's on the x. Now it's on the y in different ways. So this gravity sensor could be a really cool way to, you know, just by looking at these values, I can determine the orientation of the phone itself, which could be useful. Then Quaternion. So this is really interesting. This involves some pretty heady mathematics, but essentially it will, this is what you use if you want a static rotation value, a static three-dimensional rotation value. So you see, as I just kind of hold this with a certain angle, those values kind of stick in that. So accelerometer, gyro is only measuring change over time. This is measuring like your actual rotation in space. So how Quaternions are derived, if you have a degree in mathematics, also you could explain it to me, maybe. But essentially, it is a normally pure mathematics. It involves imaginary numbers, but practical uses we can see calculations involving three-dimensional rotations, such as in three-dimensional computer graphics. So this is a kind of practical thing. So three-dimensional. So really, if we want to like have like an Rx, Ry, Rz value, a good way to get to that type of thing is using Quaternions. It's a more dependable, more error-proof way to do that. But really quickly to show how we might do that, because strangely, okay. Oh, look, my my NDI just escaped me here. Let's go back. Capture. Oh yeah, NDI turned off. There we go. Come back. Okay, we're back. Cool. Let's go back Quaternion, hit start. Okay. So we've got 4 values here, x, y, z, w. To actually get a value in degrees, okay, so that's good. We'll just like keep quaternions here. I like that. We can use the angle chop very easily. This does the work for us. So what angle chop does, you can tell it input quaternions, output degrees. And so voila, this gives us values that look pretty familiar to us that we can use in other parameters. And we can see this goes from negative 180 up to positive 180. Right, so we got a full 360 degrees of rotation. So that's pretty cool. Okay, so quaternions change, show the static value. Accelerometer, gyro are just about change and over time. Let's look at compass. And so we really don't even need to see it in the OSC. We can see it right there. So this is, as I rotate around, this goes 360 degrees. We can see that right here. And this is where we need to be aware of our face up setting when we went into the setting down here. Compass angle face up. So that means it's expecting the phone to be oriented like this. If you want to detect the compass with the phone upright like this, you need to change that. This is still kind of working, but it's change the face up to portrait, and it will be more accurate if you're going to hold the phone like that. Pressure. So this one is measuring atmospheric pressure as well as altitude, which is super cool. So if you want to do like a DIY meteorological study, whatever, so this is what you would use. So this also shows altitude. And in the user docs, this says this is in meters. I think further information is required because pretty sure I'm more than 8.8 meters above sea level. But if I hold it like way up here, it's barely going to change. It went up a little bit, yeah. So further research needed to determine the base level of that, but it is at least showing like a relative value. As I hold it lower, just trust me, I'm like holding it low now. Okay. So that could be a cool thing to use. GPS. So obviously that's not going to change too much, like right here just on the table, but allows a lot of really cool location-based applications. 2D touch. So same thing, it can allow up to 5 touches. And gives you the X and Y for all of those. And looks like it goes basically like plus and minus 1. For Y it goes a little bit over 1. It's like 1.15 roughly. And then touch radius. So this is how fat your finger is as it presses down. So you press down with a lot of your finger or a little bit. So doing these in tandem, if we do 2D touch and touch radius at the same time, all right, we can get like, there's a light touch, there's a big touch, little things can happen based on that. We're going to look at parsing chop data in a way to control, like if certain events happen within a time period. Let's say I use the touch. If I tap it twice within half a second, do something. If I hold it and kind of keep it held for a little bit, something else happens. So that's less about the actual sensor. It's more about how you parse your chop channels. And so 3D touch beacon is not available on this version or on this phone. Proximity monitor requires some extra hardware. Mic level, very easy, very useful. So we can see. So very easy. Like level, so you can send that to all kinds of different places. And also remote control, that's another thing that's have not really used, so we can't really look at that today. But let's show an actual use case for, let's say, accelerometer and Quaternion, so how we might use this. So let's rearrange this a little bit. Okay, good enough. And let's just delete this one. So I've already made this little project. This is based on one we did a while back on materials and textures. And we've got, let's make sure this is running. So hit start. Let me reset those channels. Okay, beautiful. There we go. So check it out. I've got Quaternions controlling position of the light. So that's pretty cool. So how we're doing this, so this is the same thing I just showed. So we're selecting for the Quaternions, angle chop, and then a null. And so it's affecting the rotation of the light. But actually what I'm doing is I am using those values to change the rotation of this null comp. And then the null comp, with this little line here, this is making the null comp a parent of the light. So actually I'm going to select that. Let's get the geometry viewer here. So the light should be green because I have it selected. There you go, great. So as I move this around, I can see the light is moving around. So imagine what's happening here. The light is now a child of the null comp. So if you imagine null comp's here, light is here. If the null comp is rotating around, the light is just kind of moving inside the kind of space of the null comp, let's say. And so by still having the translate for the light, so basically I'm not at 0, 0, 0. The light is like at 5, 5 something. So that's a way we can kind of have something rotate around a certain axis, almost like a planetary orbit type of thing. So we can kind of see how that's working right there. And that creates a pretty cool effect on our space rock or whatever it is. And then we've got a little fireworks. If I shake it twice, a little particle system erupts. So that's what we looked at a little bit, because I'm using the accelerometer for this. So let's see, so accelerometer, and let's just look here. So we can kind of tell, if I freeze this for a second, as I shake it, these datas, you basically want to use a trail chop to get a sense for what are the min and max of the data. So on the X is where I was shaking it. It's basically going, up to plus and minus 4 essentially. Y is less so. Z is basically plus or minus 1. But what I did here is actually put it through a math chop. So I decided I want to trigger this thing no matter which axis you're shaking it on. So math combined channels average is averaging these 3 channels, making a single value, which we can see here now. Okay, so in that average, I'm basically getting over 1, let's say. So how are we going to do this? So if I wanted to only trigger this action of like the particles erupting when I shake it once, all we would need would be maybe like a logic. I could connect a logic, or no, actually, let's do like a trigger. That'd be even better because we can control the envelope of that. So what if I had just a direct trigger here, and let's say we trigger on 1. So whenever I go above 1. And let's do attack 0. We'll make that peak stay for a little bit. And let's just keep that 0. So sustain is still 1, and then release, let's say, will take 2 seconds. So let's see what happens. So if I just shake it once, if this value gets above 1, it's going to... There we go. So that triggered and goes back down. This slightly more complex system is counting the number of shakes within a time period. So let's say I don't want to trigger something with just 1 shake. I want it to be triggered when I shake it twice within a 1 second period. So to do that, we set up a count here. I'm actually triggering on 0.5 to make it a little bit easier. So we can see here, every time I shake, every time it goes above 0.5, it keeps counting. And then, so this right here is actually what's triggering the particles, this logic, which goes 0 to 1. I'm just going over to this particle system. And so there's a way, if you just make birth 0, so it won't emit particles all the time. It will only emit particles when you pulse this button down here. So essentially, because this value is going from 0 to 1, that functions like just a normal pulse. And my logic is triggering whenever this count is above 2, essentially. I put a 100 there, but it's just kind of, it's never going to get up to 100. It's just some like large value. So, okay, but this also gets reset because let's say I want to keep kind of shaking this, but when I put it down, I want it to go back to 0, right? So how do we do that? So that's where this trigger comes in, where it also triggers for 0.5 seconds. It will stay at the peak, which is 1, for 1 second. And then if there's no more shaking happening, it'll go back down to 0. And this chop execute dat is saying, so I've got, looking at trigger, on to off function is turned on. And inside here, I've got this, it's looking at the count chop and pulsing its reset pulse. So whenever this trigger goes back down, hello, come back. Whenever this trigger goes back down, it's going to reset the count, which we'll be able to see right here. And that's what resets the count right there. Great. So it really doesn't matter if I keep shaking over and over and over and over. This is going to keep counting. I'm not emitting new particles, though, because it's only going to emit when it goes from 0 to 1 over here. And if I only shake it once, you can see that was 1 shake. Didn't trigger. Okay, great. All right, so maybe that's good. You can imagine other cool use cases for all those other sensors, but that is an introduction to Zig Sim.